Flash attention. With all these large language models and self-attention driving a transformer model, the idea behind flash attention is to dramatically accelerate the performance of these models using an approach that I have personal experience with. I have done this myself. The idea is to create a more efficient pipeline of transformation of the matrices and data as the input data is being transformed through each of the layers. And guess what? It sounds complicated because there's a paper and there's a whole bunch of different authors associated with it, and it says flash attention, fast and efficient memory extraction, or exact attention with IO awareness. It's like, whoa, what's going on here? We can actually bring it down to we can make this really simple. This diagram, boy, does it look complicated, but really the really important part is right here at the very end. There's this little chart here at the end. Let's zoom in on that. All right, so when we're building a language model or any AI model in general, what you have are a series of transformations of input. So your input data is, say, text, like words, sentences, like large paragraphs of text. That gets transformed into floating point numbers, right? Something that mathematically can be represented through a series of math functions. The big one here is going to be matrix multiplication. You're also going to have training algorithms here that help converge and generalize outputs. And each of these steps are different functions. And you've got PyTorch here. PyTorch is going to interface via CUDA and other GPU backends. That is going to require a lot of memory transfer between each of these phases and each of these steps. And there are pipelining procedures that can occur in PyTorch. PyTorch 2 does a better job of this. However, it's still not perfect because there are different phases of transformations as you transform every single unit that's being computed mathematically, every single weight and coefficient. So when we're looking at this here, we see essentially they're all combined. What it does is it merges all these different mathematical equations into one step. Doesn't that sound a lot better, a lot faster? Because what you get to do is compute these units all through one pass on the GPU, sort of in a fused kernel. I've done this firsthand and seen insane performance improvements. And it doesn't have to move memory around. It's just computing a number based on these algorithms, and then it does a final merge on the output, and that data can get copied through texture memory copy back to the CPU, so then you can update the model weights. Doesn't that sound a lot better? All in one. And that's like the whole deal. And they call it flash attention when they should just call it good programming. I think it's like, flash attention, it's a new technology. No, they just made the algorithms more efficient. They just created one giant CUDA kernel that gets compiled and passed over to a compute unit, and then as you pass data into it, it can compute that floating point number in one giant phase across multiple cores simultaneously, and it doesn't have to use any additional memory passing. And that's where the speed comes in. So we look here, the memory passing can be very, very slow. So on the CPU range, you're going to get you can get faster than 10 gigabytes a second. Now that does sound really fast. That's pretty fast. That's pretty fast memory. But you have a terabyte of memory, and it takes a lot of seconds, minutes to get data to load into memory. But in a GPU, you get a terabyte a second. That's a lot. That's really fast. So that means you can fill up the GPU memory nearly instantly. So if we can keep all of the algorithms in GPU memory, and we don't have to transit back and forth, and we can leverage as much of the SRAM as possible, guess what? You're going to have a much faster language model, like a lot faster. Like, look at that, it's like 100x. That's 100x faster. With flash attention, we can use it to accelerate our machine learning models. And specifically, this is going to be a transformer with self-attention, right? Where we can use scaled dot product attention and accelerate that entire pipeline, because the whole idea behind flash attention is just an efficient mega kernel, an all-in-one CUDA kernel that is written and optimized for PyTorch, libtorch, right? And specifically, we're not looking at the full transformer. We're looking just at the attention layer, which is a pretty substantial attention layer, I would say. And what I'm noticing here is so here, QKV is your input data, right? So this is going to be your input data to the model in general, right? What is your input data? Is going to be your text data, right? Your sentences, your numbers, your tokens. This is going to be, say, a word, a big sentence. Even you could say, this is the input data. The main function implement, it's scale.product attention. That could be your input data, right? A sentence. These words will be transformed into tokens, which are going to be integers, right? Number values. A dictionary, essentially, with an index representing the word in the dictionary, right? So this word right here might represent, number 42,000, right? This word right here might represent the number 300 because that's where it is in the index of the dictionary. Once these are converted to tokens, you essentially have your input data because now it's numbers that you can throw into an equation, a mathematical model, which is what machine learning is in the first place. And the attention model with scale.product, it looks like this. It's really quite simple. It's all about self-attention. The model can attend to itself so it can understand the input data in context as it's, right? Because these words, where they are located to each other, have meaning, right? Where this word main and the word product could have some significance, but these words combined has a much more significant meaning. And so you want to attend these words with each other. Now, Q and K and V, they're all the same. It's the same sentence. So it's this sentence here, and it's just an array. It's a simple array, right? So then we can attend Q and K to each other. Q and K typically have like a positional encoding, so you can extract like every other word might have an interesting component as you're representing it next to each other. And then V typically has no positional encoding. It's just the original tokens. So looking at the softmax, self-attention, right? Flash attention. Here is the main function. All in one, this is going to be your most important function here because it's all packed in one giant kernel. We're going to do the matrix multiplication on Q and K. Then we're going to scale that with a scale, a floating point. The default is going to be the square root of the dimension of the number of heads. Under 1, the dot product scaling aspect. And then, of course, softmax is going to be very useful from an output perspective as it helps normalize the output. And this is important. You don't have to do this. Like, it's not mandatory. You can skip the softmax. However, you will very much potentially, depending on how you've set up your dictionary, have a large range of potential outputs that could significantly blow out the meaning. So what you want to do is sort of compact all that output and normalize it. It's called a normalization function. So that way, even if you have a really big number as the output data, it'll always be between 0 and 1. And that really big number, relatively to all the other output data, it will always add up to 100, right? All those numbers, all the outputs add up to 100. So this is normalizing, which it helps a lot. You will want it. It's not required, but it helps. So this is it right here. Look, it's really simple. This very straightforward, isn't it? Like softmax, matrix multiplication, scale it, and then another matrix multiplication. That's it. Oh, but it requires so much code in order for that to work. It's ridiculous. We get a few extra bonuses here. It also includes a dropout for training purposes. You get, is that linear bias? Attention with linear bias. It adds, look at that. This is cool. So they give you a few extra bonuses here that you can use, which are more modern approaches when you're using a transformer or applying your attention, whether to apply causal attention mask. All right. So for autoregressive modeling, that you could apply a mask to the output, and they do it in the CUDA, which is great because then you don't have to do that in the CPU layer, which sort of throws away half of the typical mask that you'll see. It will zero out half of the output matrix in a diagonal fashion because there could be some symmetry on either side. And that's important because when you're multiplying Q and K, you're going to have symmetrical information because you're iterating attention between the word the needs to be attended to the word main and functions and implemented. And then you do the same here with main and the. You can see there these two words will very quickly be the same output because you're self-attending every word to every other word, but you'll have duplicates. So you can apply a mask because you don't need to bother multiplying those numbers again further down the line because it's repetitive. This one I'm less familiar with. It's window size, implementing sliding window for local attention. Oh, okay. So this could be the attention sizing, which might reduce. So if you have a very large input, you could have a smaller output because you're looking at more. Potentially, maybe instead of a 1-by-1 where you're comparing it, you might be comparing 2 words to 2 words. Maybe. I mean, that's what it sounds like to me. Attention with linear bias is pretty straightforward. It's just scaling it based on. All right, attention with linear bias actually is a positional, sort of like a positional encoding method, which is actually pretty great because one of the things that we notice is that it didn't mention the sort of cosine position alternating tokens, which is a common, a traditional positional encoding. You can use a scaling linear bias positional encoding method. And so you don't have to use traditional position embeddings, and then you can have the GPU code this for you. Ooh, okay, so this is why it's even faster than I thought it was before. And the good news is it looks like there's a default. So you can just pass in QKV straight up as is without having to worry about pre-positionally encoding them, usually in the CPU, right? And you need to do that in a CPU because it's an alternation. You could do this in CUDA, but then you're going to have to add another layer on top of it and then remerge it, and there's some extra work to do there, which is tricky. There's also a deterministic backward pass implementation, which uses more memory and is slightly slower. Let's take a quick look at the performance differences that we see in the significant gains of flash attention. With an all-in-one mega kernel in the GPU written in CUDA, we see that flash attention, specifically flash attention 2, is significantly faster. And it makes a lot of sense. Why? Because you're merging all that logic into one giant, math program, and that program can run on a GPU inside each of its cores without it having to reach back out to memory and pass data around. So you're going to get the most potential performance, and you're going to make that GPU really, really toasty because you are going to leverage all of its compute power without any sleep cycles waiting for I/O. And you can see here it's significantly faster. So we're looking specifically, we want to look at the best possible scenario, most common scenario too, and that is going to be in the case where we are looking at a full attention forward pass or back pass. Mostly a forward pass, where forward attention and backward speed on an A100 with 80 gigabytes with the causal mask and 128 attention dimension heads. And we can see here as your input sequence length goes bigger and bigger, we see a nice increase in performance gain capability as the distributive capacity of flash attention 2. It's going to just rise above the rest because of its ability to merge all these tasks in one. We're going to see slightly less interesting, still some performance gains here compared to PyTorch as is, right? The standard PyTorch, where it has to do some of the work in one of the math functions like matrix multiplication, then it moves over to dropout, then it moves over to softmax. If softmax is even available in, it might not be available, right? They've implemented softmax with flash attention inside of CUDA, from what I understand. I'm just trying to think of how they go about, because when you're working with say you're working with a shader and you're working with a pixel with RGB values, maybe alpha as well, so you have a four-dimensional array. That's all you really have access to for each core, just basically one pixel at a time. You understand its position and location within that texture, and you also have the values, the RGBA values, but you don't know any of the others. You don't know anything else about any of the others. So it's possible that we could be leveraging one of these channels to indicate a max value, so that way we understand how to scale it in a softmax perspective. So there's a potential performance gain there, and that's really where flash attention comes into the win, is being able to run all that logic in the GPU core kernel directly without you having to jump back over to the CPU memory, because that latency on the I/O is what really gets us. That's where the next evolution comes in, and this is just for the attention layer. It's not talking about the entire transformer. Imagine how cool we can get if we implemented a mega giga kernel all in one super core, super kernel. Oh, that would be so cool. So they succeeded with flash attention and just the attention layer. The number of teraflops a second is just phenomenal. You just compare this, like 23 teraflops versus 100, right? That's a 5x. We're seeing like 5, 10. Oh, this is beautiful. And we're seeing roughly a 5x performance boost just using it as is with this, which is just phenomenal. That's just over standard PyTorch. And with and that's flash attention 2, right? But flash attention 1, you still get a 2x improvement. It's amazing. These are phenomenal numbers. It's just so good. And if we take a peek, let's just simplify the chart here really quick so we kind of see a little bit better. This is running on the H100 with 80 gigabytes of RAM. So, a nice beefy GPU here. We see that PyTorch does a pretty good job. That's still a lot of teraflops. Don't get me wrong, right? 62 teraflops. That's a lot of teraflops. But when you compare that with Flash Attention and Flash Attention 2, you would much prefer to leverage the Flash Attention mega kernel over PyTorch any day. I mean, just look at this. Fantastic performance gain. So what we can do is we can leverage this approach and this technology for more of the layers in a transformer model to significantly improve the performance and reduce the wasted time it takes as layers transit in between each of the mathematical equations need to run on all the matrices. Oh, check this out. We've got something new. We got a new Flash Attention minimal that we can take a look at and look at the CUDA code, which looks a lot like C++. I think actually it might just be. It is. Oh, it really is its own language. It's CU, right? So we've got a CUDA language. And what we can do is take a look at this Flash Attention minimal. It's an implementation someone wrote in CUDA that takes advantage of the forward pass only, not the back pass. Obviously, back pass is going to be a little more intense because there's back propagation, which requires the inverse, but you also have to store the gradients and remember the gradients as you're going backwards. So that way you can use those gradient informations, right, those matrices, to find the deltas of how far off the output was so you can train the model. This Flash Attention minimal does not have that part. It only has forward pass, which allows you to run inference, right? So you can just ask questions for the model and the model will give you an answer. That's all it can do. You cannot train a model with this approach. You'll need more than 100 lines of CUDA. But if you look at the profiling really quick, taking a look at just normal PyTorch with CPU and CUDA time, the profiling on manual attention, just regular attention algorithm, and we know that algorithm looks like this. Very simple, straightforward algorithm. Softmax dot product with Q and K, which is self-attention of a sentence, and then you scale it based on the number of heads, I think it was. Right, the square root of the number of dimensions over under 1. And then you apply softmax to that matrix, and then you dot product, again, this output with the attention of the sentences again. So it's pretty straightforward algorithm, really powerful self-attention, right? And look at what you get! A significant performance improvement. Profiling the minimal flash attention. What is this? What is that speed? All right, 4 milliseconds compared to like 52 milliseconds. All right, that's like a 13x improvement. Wow. That's because what happens is you put all of the mathematical operations into one mega kernel rather than, so here's obviously the drawback is it can only do this one thing really well, right? It's like a super function that takes a bunch of common algorithms into one and makes it one giant kernel that can be used and installed on all the cores of the GPU. So when you're putting the input data in, it's going to run all of those algorithms together in one pass without having to transit memory, and which that's the slow part, the I/O. Taking a look at our CUDA. Oh, nice. Look at that. Okay, so they give us almost everything that we need here. It would be nice if the variable names were a little bit extra. Obviously, we're fine with Q, K, and V because we know that's just the input tokens. Do we have attention with linear bias that we got with the other one? No, doesn't look like we have that. One thing I'm noticing here straight off is that since this is only a forward pass kernel and there's no back propagation, it seems odd that we have batching, because if we're self-attending and it's sort of expecting to do what large language models do, where they run through one pass, get the output in a full transformer, and then append the output to the input again, and then run it through again to get the next word, right, the next token. You don't need to batch that. Batch is only really good for training perspective. So this could be, fairly interesting from a future perspective to support batch, but this is like one optimization I noticed. So we have our thread and block IDs in CUDA world. This is going to give us information about where our current core is running within our kernel, right? We've got our forward kernel. It's like which one of these cores on the GPU are we located in, and we use that information to be able to access and perform mathematical functions on each of the essentially pixels, right, of the matrix. And the matrix is going to be a representation of our input data, which is the sentence and the words, right, the tokens. And each one of those, each one of these threads is going to be able to work just on that one word at like that one input at a time, because you don't want to do that's how like the parallelization work, right? That's how it works in a GPU. You're able to split out all the work across multiple cores so it can run simultaneously, like all at once. Let's do a matrix multiplications. Let's do all that work all at once. And then we merge the output. Boom, there we go. Performance improvement. That's really where the power of the GPU comes in, is because it's sort of breaking down. It allows you to write code to break down as much as possible the amount of work into a finite amount of space. You want to be able to spread out that workload and, you know, get the most out of it by making it as small of a chunk as possible. Because then you can just keep scaling up the number of cores in a GPU, and you can add more parallelism, and then you get really, really fast output. So I see we're using SRAM here, which is going to be really powerful. We want to store all of our all of the input data, right, through our QKV. We want to store that in SRAM, which is a small amount of RAM, but guess what? It's really fast. How fast? Oh, let's see here. We saw that earlier. We are seeing upwards of 20 terabytes a second. That's a lot. You get 20 megabytes, but this is going to be, that's not a lot, right? That's not a lot of memory, but it's more than enough for the input data, right? So you're going to have like maybe a document, and you're going to tokenize that document, which is essentially compressing it into a dictionary. And so you can have a large input size using SRAM alone, and SRAM is going to give you the extreme power. SRAM is shareable as well. So we're going to move all of that input data into SRAM, and now all of our cores can access the input. This is so cool. So now we can even do, is softmax going to be in here? They better have it. That better be here. Okay, yep. Yeah, all right, so we're getting our max. We need to find the max. We definitely need SRAM for this. We need to look over all the SRAMs. We're going to get to find the maximum number, which allows us to scale. Oh, yep, here we go. Softmax. Boom. We got ourselves a softmax right there. I don't want to read this anymore. It's just too like all of these. It's just a bunch of variable names. It's hard to keep track of what all this is. This looks like it's okay. So it's finishing off the self-attention scale.product here, leveraging with access to SRAM, which is really powerful, really performant memory. Something that I don't necessarily like is the need to use sync threads here, such that I mean, I get it. I would say probably run that once on import for the import data. But inside of a for loop seems problematic to me. I don't like this implementation. I feel like the kernel can be significantly improved if we eliminate the need for sync threads altogether, especially inside of a for loop. But I like this part. I really like this part. So we go to forward pass tensor with QKV. This is really powerful because this is the tensor interface that you're going to get in PyTorch. Just a simple forward, and all you have to do is pass in QK and V, which is the input data, right? And then you get the output as it executes the kernel. What work does it do? So what work does it do here before it passes it in? So on the CPU, we calculate, we populate matrices. We create some matrices, and then we're going to pass those matrices to the GPU's memory. And then we do some preparation to get the memory amount size. Looks like we also get the softmax scale. What are we doing here? All right, we're getting dimensions, so we understand what how big the matrix is going to be for the input data. I like this. This is nice to have. It really is, because when I pass in my input data, I don't want to also have to pass in all this extra work that the function could just determine itself based on the input data alone. I don't want to have to say it's this size and that size. Thank you for doing this for me. And then once SRAM is all populated and we have a little bit of extra information here, we run the kernel GPU function. That's this giant math equation up here. And then we get the output. O is a data pointer. So if we weren't sure before, we are now. We can see kind of the idea of a minimal flash attention implementation in CUDA directly. You can see that it just merges together a bunch of functions into one giant mega kernel, and it allows also it puts all the input data into as shared memory. That's really, really fast. We could make some significant performance improvements here. I do see by eliminating sync threads. Overall, that's the whole idea. Why does flash attention so effective? It merges multiple operations into one kernel, so you don't have to waste time on I/O. That's immensely powerful. It's really fast. Now imagine we can do that for all the rest of the phases, our transformer model, making it even faster. And that's possible. We could totally do that. So this proves that we can do that with the rest of the thing. And imagine we just did one mega super kernel. Now we're approaching the future. Oh, and just in case you were wondering how PyTorch can import this forward past main.cp, main C++ file essentially just includes torch extensions and identifies the prototype, and then it runs pybind. Neat! And then we import, okay, this is kind of cool. So we take the PyTorch extensions, the C++ extensions, we import the load function, and then we get ourselves that forward pass C++ main definition through the flag. Yep. And this minimal attention function is now our forward pass. And just in case you wanted to see what the difference was on terms of how much Python code you need compared to how much C code you need and CUDA code you need, it's a lot more. I mean, just look at this. Isn't this amazing? It's just, a few lines of code compared to over 100 lines of code that's required to get it to work on a GPU.